something, but I need to, we need to get moving here. So I'm gonna start with some homework question.
Also, I have a separate one.
Okay.
My OneNote keeps like shutting down, and I forgot the thing where you told me to do one time that missed it.
Yeah, we'll talk after class. Yeah, absolutely. So again, homework questions, we'll start with that. At this point, we've talked about, we've done stuff from 3.9, 4.1, and 4.2.
3.9, 4.1, and 4.2 are all due on Sunday, right?
Well, I'm gonna be real honest. I'm not looking at anything until I come back to work.
So if I do it like during break, is it like okay?
I think it'll be totally fine.
Perfect.
I won't notice.
Okay. Okay.
Beck.
Sounds like
7 from 4.2.
4.2, number 7, absolutely. So this is a graph, right, that we're looking at? Is that right?
Yeah.
Okay. So it says, use the graph of f to estimate the values of c that satisfy the mean value theorem on this interval from 0 to 8. Well, I'm going to start by just kind of like drawing in the mean value. And then I'm going to look for places where the tangent line looks like it would be parallel to that. So maybe one here, which looks like at 3, and then maybe one like right there that looks like 6. That's all I'm doing. Just using my eyes.
Okay, thank you.
There's nothing to calculate. There's nothing. I'm just kind of like drawing in that secant line, and then I'm just like, okay, where could I draw a tangent line that looks like it's about the same slope? That looks like it. Yep. That's all you need to say. I think you would say C in this case because it says values of C, but nothing fancy, which is a relief, right? Oh, it's that simple? Yeah, it's that simple. Sometimes the picture ones can be the simple ones. What else?
Could I ask you a full point?
Sure, of course.
Could you do number 5?
Okay. So 4.1, number 5. Another graph one. Cool. Okay. All right, so it says state the absolute and local maximum and minimum values. So number 5, let's start with the absolutes. So the absolute highest point is here. So that's 1, 2, 3. And maybe let's write down a point. I don't know how they asked. 2, 3, 4. So that's happening at 4, 3. I guess if it wants the values, it would be 3. If I look at our lowest overall point, it's here, but it's an open. So is there an absolute minimum? There is not. Because you can get as close as you want to -1, but never actually get there. Now let's look for locals. Start with maximums. So here is a relative high point, but it's open, so it can't happen. Here is a high point. That one works. An absolute max is also a local max. So really just 3. And then here would be a relative high point.
I thought you can't have that.
Well, if I take some open interval with that point in the middle, is that point still the high point? Yes. So it can happen there. So what is that? 1, 2, 3, 4, 5, 6, comma 2, or really just 2. Feel okay?
6, 4. Graph doesn't start until I get.
Oh, yeah, that's 1. So this, yeah, so these are all, my numbering's all off. So that's 2, 3, 4, 5. So that should be 4, 5. And that should be 6, 4. Thank you. I had the right idea, I just couldn't read that's a Mr. Kulik mistake if I've ever seen one. You do the problem entirely correct, but you misread. Ay, ay, ay. All right. Now, our minimums. So I see a local min here and a local min here, and that would be it, right? So that looks like 2, 2, so 2, and then 5, 3, so 3. Is that okay? Sure. So, is there an absolute maximum? The overall highest point is open, so can't have one of those. Absolute minimum, do we got one of those? Well, the value is before 1. I'm just going to write down the values, though, because that's really what it's asking for. So I'm just writing down the y coordinate. And then if I want local max, so those ones, right? So that was 2, 3, 4, and 3. And then my local minima, I do have one there. If I take that interval, that is the lowest point in that interval, right? I think that probably counts. And then the absolute minimum is also a minimum. Let's grab the answer book and take a look at that. That would be the one that I would be not 100% sure on, but I probably think that's right. I'd be surprised if it wasn't, because it meets our definition. Okay, is that 4, 1? Okay. 3, 4, and 6, 3. Good. 2, 2. Yep, and 4, 1. Good. Okay. Yeah, so I was right. Anybody else? Okay. Yes.
Sorry, can you do 15 for 4, 2?
15 on 4, 2? We are. I know, seems like a bad idea when so many people are gone, but I gotta do it. Let f of x equal yada 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 show that there is no value of c in 1, 4 such that the mean value theorem holds. Why not? Well, here's what I would say, Beck, is f of x is this, right? The domain for that would be like 1 to 3 and then 3 to 4. So it's not continuous. F is not continuous over its domain. So mean value theorem doesn't, that's one of the conditions I need for the mean value theorem. Additionally, if I take the derivative, that's not going to be differentiable over its entire domain because the F wasn't. So I lose another potential part there, so we don't meet the conditions.
Okay, thank you.
Yep. So it's just like a, do you know the hypotheses
Right.
for the mean value theorem to apply kind of question. Uh-huh. 70?
Yes.
Okay. Oh, I didn't mean to press there. I want to press over here. Sure. Ooh, physics. An object with weight W is dragged along a horizontal plane by a force acting along a rope attached to the object. If the rope makes an angle theta with the plane, then the magnitude of the force is F equals yada, 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 where mu is a positive constant called the coefficient of friction, and where theta is between 0 and pi over 2. Show that F is minimized when tan theta equals mu. Okay, so if I want to find the minimum, I'm going to start by looking at the derivative. So to take the derivative of this, what do we need to do? Very good. So it's the quotient rule is the bottom times the derivative of the top what do we differentiate? Probably time, I suppose. And then the top times derivative of the bottom over the bottom squared. Okay, so I'm just going to distribute some stuff through the numerator because that's really the part, when I said equal to 0, that's the only part I care about. I note that the denominator can't be 0 because in the first quadrant, sine and cosine are both greater than or equal to 0, and they're not equal to 0 at the same time, so I don't have to worry about any extraneous solution there. Okay.
Oh, no, no.
All right, so let's say that we factor off a mu. Kind of feel like I don't want these differentials in here. Let me look at what they did here real quick. But this is the right idea. I'm going to cheat a little bit because it feels like I should have put these differentials in here, but it also feels like that's all getting in the way. Yes, of course. Yeah, okay. All right. So that's my fault. So f here is a function of theta. So I'm going to erase all of this stuff here. I mean, there's probably going to be some minor updates if you want to just hang on to it. So when I do this, I'm doing my derivative with respect to theta, which is why I end up with a bunch of stuff I don't want. Keep in mind, W is the weight that's being dragged. Is that changing? It's a constant. And mu is a constant as well. So that's where we goofed up. So if I have the bottom times the derivative of the top, that's just going to be 0. And then if we have the top, what's up? Which makes all the difference in the world. So again, we'll just take the top and set that equal to 0. Distribute that mu w through. Actually, let's not. Let's just apply the zero product property here. Since mu w is a constant, I can just ignore that, right? Then we'll just add the sine over and divide by cosine, which is tangent.
Oh yeah.
And I think that's what we wanted, right? If you set the constants equal to 0, there's no solution to that, right? Because those are just numbers. Or you could divide both sides by and just get it out, like blow it up out of there. I just ignored this because it's a constant. Be like if there was a 7 and I had in parentheses x squared plus 4 and then equals 0. I can just ignore the 7, right? It's a constant. Can't contribute to the solution. There is a little loose end here, though, which is all I know is that the derivative is 0 when mu is tan theta. How do I know it's a minimum as opposed to a maximum, right? Or nothing at all, right? You could have, the graph could do something like that where you have a derivative of 0, but it's not actually a minimum or a maximum. So there is still one more little loose end here. So what I want to think about here is, let's see. Let's see. Now this gets complicated. What did they do? Yeah, fine.
Yeah, honestly.
You are?
But this is significantly more than I got.
Okay.
I'm happy with this.
Yeah. Okay. If you ask me again, I'll look at this over break and come up with a good explanation as to how I know that's a minimum, but it just feels like I'm going to spend 10 minutes stumbling around and then waste 10 minutes.
It's okay.
Well, Beck was going to ask about it. I could see his hand coming up to be like, okay, that's 0, good, I agree. But the minimum is more than just derivative equal to 0. And that the explanation is, I mean, it's here, I can read it, but sorting out the reasoning behind why they did what they did would take me more than a minute. But I'll come back and look at it. Maybe I'll just post something drop something into the OneNote or something. Okay. Let's do 4.3, eh? So most of what we've been interested in so far in chapter 4 has been finding these maximums and minimums, right? So we're going to continue kind of that discussion, looking at what can we do to kind of formalize finding these local mins and maxes. Because in 4.1, we developed a method for determining our absolute mins and maxes that required a closed interval, where we just tested the critical values and the endpoints of our interval, and then picked the biggest one was the max, and the lowest one was the min, right? But the locals provide a little bit more of a challenge because we can have lots of local mins and maxes, and it's not entirely obvious just from the value of f whether that is a min or a max. So let's take a look at what really the first derivative and second derivative can tell us about f and the location of these local mins and maxes. So we're going to start with the definition. We're going to define f as increasing when its first derivative is positive, and decreasing where its first derivative is negative. Same idea, right? If derivative is slope, increasing we'd have a positive slope, we're walking uphill. Decreasing we have a negative slope, we're walking downhill. That should be real intuitive, not much of a stretch there. So if I wanted to figure out where a function is increasing and decreasing, what am I going to do? I'm going to take the derivative, set that equal to 0. So in this one, to solve this, I can factor out an 12x and then if I factor that, I have x equals 0, x equals 2, and x equals -1 as solutions. So I'll draw like a sign diagram. And then we pick like a test value of x, and I'll plug it in to my derivative. I'm going to use the factored form. When I plug -2 in for this, I get negative, and times negative, and then times negative. So I know that part is negative. And then maybe I'll use a test value of -1/2. So when I plug that into my derivative, I get negative times negative times positive. So that part is positive. From 0 to 1, I'll do a test value of +1/2 here. So that's positive, that's negative, that's positive. So that's negative. And if I do a value greater than, that's supposed to be 2. So say I'll do 3, and that's positive everywhere. So if I look, these are the two intervals in which we're negative. So that's where we're decreasing. And that happens from negative infinity to negative 1, and then from 0 to 2. And then we're increasing from negative 1 to 0, and then from 2 to positive infinity. Of course. Does that feel all right? It was the same kind of method we used to solve like a polynomial inequality way back in pre-calc. Looks like the same method. It is the exact same method because all we're really doing is taking the derivative and then solving a polynomial inequality in this problem. It's not a graph. This is called a sign diagram. So all I did was I labeled my places where the graph is 0. So those are the only place where the graph of f the graph of f prime could cross the x-axis. So if I pick any value in between those numbers, whatever that f prime is doing, whether it's positive or negative, it must be there that entire interval, because if it changed, it would have had to cross, and I know I don't have any more crossings.
Okay.
So I just picked something that was less than negative 1, plugged it into f prime, and saw what I got. And I got a negative. And all I did there was like negative times negative times negative.
Oh, okay.
That's a negative. So I didn't actually plug it in. I did it like intuitively because I'm getting ready to take a time test, potentially without a calculator. And I want to look for the little hacks that I can use to not have to do a computation if I don't need to do the computation. I don't actually care what the number is. I just want to know if it's positive or negative.
Okay.
And then I did the same thing between negative 1 and 0, and the same thing between 0 and 2, and the same thing from bigger than 2. And just plugged them in and just positive, negative, whatever. Is that okay? Good. Okay. That leads us to what we'll call the first derivative test. This is the foundation for it. Suppose that c is a critical number of the continuous function f. Remember, critical numbers can be where the derivative is 0 or where it doesn't exist. So the two possibilities for critical numbers, where the derivative is 0 or where it doesn't exist. Have to be careful about the does not exists. We forget about those all the time. I do too. So if the derivative changes from positive to negative at one of those critical numbers, so we're going from increasing to decreasing, that's a maximum. If we change from decreasing to increasing, that's a minimum. And if there's no change, if it's, it goes increasing to increasing or decreasing to decreasing, that's not a local min or max. It's just nothing at all. Everybody cool? Okay. And here's some pictures kind of detailing that, right? Where we go from increasing to decreasing, that's our maximum. Decreasing to increasing, that's a minimum. Increasing to increasing, that's nothing at all. And decreasing to decreasing, that's nothing at all. So if we wanted to find the local min and max values from f in our previous example, we're going from decreasing to increasing at -1. So that is a minimum. Then we go from increasing to decreasing at 0. That is a, and then decreasing to increasing at 2. That's a minimum. So once I have the sign diagram deciding what they are, piece of cake, right? All we're doing is looking at stuff positive or negative. In the interest of time, I'm going to skip this one. It's annoying because I think you have to use your calculator to do it, or you have to use some trig intuition, because I want to get through stuff. If the graph of f lies above all of its tangents on an interval I, so if that's what you're seeing in this picture, f is the blue. See how the blue is still kind of above all of its tangents? We say that that graph f is concave up. And if it's the reverse, if f lies below all of its tangents, we say that's concave down. I think about concave up as it catches water, and concave down as water would run off of it when I visualize it. But that's the technical definitions there. So if I look at this piece here, we are concave up from A to B, and here we switch to concave down. Maybe I'll just do this. And then here we switch to concave up again, switch to concave down, still concave down, and then switch to concave up. These points where we switch concavity between concave up and concave down, those have a special name. We're going to call those inflection points. Now, we can test for concavity. Instead of using the first derivative, we use the second derivative, because that'll tell us how the graph is bending. So we say something is concave up if its first derivative is positive, or second derivative is positive, and concave down if the second derivative is negative. Blah, 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 blah. I don't care about that. And we say that we call some point on our curve an inflection point if we change from concave up to concave down or concave down to concave up. There's a change in concavity. So if we wanted to, we can use this kind of information, to sketch a possible graph. So if I were given these conditions, I want to sketch a possible graph. I know I need to care about 1, -2, +2, and that looks like the specifics there. So from negative infinity to 1, my graph is increasing. So we're going like that way. And then after -1, we're decreasing. So we're kind of going that way, right? And then from negative, so let's do this. I'm going to do some highlighting. So we are increasing there, and then we're decreasing there. That'll be easier. And then here, we're concave up. And over here, we're concave down. Oops, we're concave up in 2 places, right? And then we have the end behaviors here. So at negative infinity, we need to be going and following -2. And at positive infinity, we need to be following 0. Everybody okay with what I did there? All right. So now I need to draw something that's concave up and increasing all the way to 2, in which case we're going to change and become concave. Oops, I still need to be increasing, but I need to change to concave down, right? Okay, concave up. We change to like, concave down. We still need to be increasing. All right, let's just try to draw that. There we go. That looks good. And then we switch to decreasing. and back to concave, oops, we're going, doing something like that. So if I look here, this would be like an inflection point, and this would be an inflection point, and I kind of goofed because my local maximum should be over here, doing something like that, more like that. So just got to kind of piece it together. It's hard to vision it in your head. Sometimes it may take a try or two, but I like to make sure I've read everything first and kind of, decide the places on the graph that matter, where the changes have to be happening, and then kind of figure it out. So that we have what we can do now, in addition to telling concavity with the second derivative, we can also check for if a critical value is a maximum or a minimum using the second derivative. This is called the second derivative test, or sometimes the candidate's test. So if we have a critical value where the derivative is 0, or first derivative is 0, and the second derivative is positive, that's going to be a local minimum. And if the first derivative is 0, but the second derivative is negative, that's going to be a maximum. So this one is weird because it seems like it should be the opposite, right? So the last couple here are examples. So let's say we have this curve. So let's say we want to do y prime. And let's set that equal to 0 to find the locations of the maximum and minimum. Everybody okay there? So another way, other than doing my first derivative test, where I look at the whether the graph is increasing and decreasing, I can calculate the second derivative, which is pretty easy, and look at the second derivative at 0 and at 3. 9 times 12 is 108. And then 3 times 20 for 72, so that's positive. So at 0, that's nothing, right? Since the second derivative is neither positive nor negative. So that tells us that that critical value is not a maximum or minimum. So it should look like something like that. And then 3 is a minimum. Now, if I wanted to sketch the curve, well, it should be pretty easy to see that I have x-intercepts at 0 and 4, right? Can you guys see that? 1, 2, 3, 2, 3, 4. Yeah or no? Well, if I set this equal to 0 and solve, right, factor off an x cubed, and then I have x equals 0 from the x cubed and 4 from the x minus 4. And I can see that before 0, if I plug a negative value into this, into the first derivative here, I'd have positive times negative. So we're going to be decreasing. all the way up until 0. And it would be positive because that should be positive when I plug a negative, and that'll be positive. So I should be concave up as well. So it's going to look like that coming in. Once I get to positive values, let's put 3 in there. So we'll pick that as a minimum. This is going to change concavity now and still go down to our minimum. And then from 3 on, we're going to get negatives again, right? So from 0 to 3, that'll be positive. But after 4, wait a minute, what is it? This is times 3, so it's going to be, and then we're start increasing again. Yeah, and we'll do like one of these. Back.
Sorry, how did you know 3 was the minimum?
Because this was greater than 0, so I used my second derivative test. Because when I solve this thing equal to 0, I get 0 and 4. At the left side over here, because it was decreasing. If I plugged in a negative number into here, I get a negative number. So anything from less than 0, if I plug into the second derivative, gives me a negative, so I know it's decreasing the whole way. Is that okay?
You did a negative number.
Yeah, because I had to pick something less than 0, right? So just like, I just thought of a general negative because that was good enough for me. You know, like, again, like the goal is to avoid having to like manually plug numbers in because it just slows it down. If all I care about is positive and negative, I can just kind of do some sign crap, you know, and it's usually pretty obvious. I think we're almost out of time here, so I'm going to stop because the next 3 problems are like the exact same 3 problems. But this is the idea. This is the last of these, like, how do I use the first or second derivative to tell stuff about f ideas. The last section we're going to do before the test is going to be L'Hopital's rule, which was a way to deal with some hard limit problems in an easier way. You'll like it. It's good. So that's that. I have a key for the multiple choice questions that I put on. I'm working on the free response question key right now. I've done like 2 questions out of the 4 or something, so I should be able to get that up hopefully today before we leave. So if you're on break and you want to start looking things over or like working on your open homework sheets when you have a couple of days off, that I want that to be there for you guys.
We're allowed to use like the MCQs on our open homework, right?
Yes.
We read a couple down.
Yes, of course.
Thank you.
Sure.